Okay, it says construct the seventh order Taylor polynomial and the series. That means we have to write the summation piece centered at 0. Okay, first thing I'm going to do is write the shell of my polynomial. So it's a seventh order, so I'm going to call it p sub 7 of x. And I'm going to write the shell of it. I'm going to take my derivatives later, so I'm going to leave these numerators blank. That's where my derivatives are going to go. My first one is going to be a 0 factorial x to the 0. Derivative over 1 factorial x to the 1. 2 factorial x to the second. 3 factorial x to the third. 4 factorial x to the fourth. I'm gonna run out of space. Oh, come on. Boom. Yes. Okay. So this, I am like so close to being home. If you're on an AP exam, this is the first thing you should do because this shows that you at least know what a Taylor polynomial is. So even if you run out of time and you have to guess at what these numbers are, you've written a Taylor polynomial and it is seventh order and it is centered at 0. I'm just saying, time. Okay, so now all I need are the derivatives of sine, and I need them evaluated at 0. So this shouldn't be too terrible. Change my mind about what I want to write here. Okay. All right, so the first thing I'm going to do is take the derivatives, and then we'll worry about evaluating them. I think that's easier. Okay, so the function is sine x. So my first derivative, cosine x. My second derivative, derivative cosine x, negative sine x. Third derivative, negative cosine x. The fourth derivative, derivative of cosine negative sine, so positive sine x. And you may notice that we are back where we started. So the fifth derivative is going to be cosine x. The sixth derivative, negative sine x. Whoa, oh no. Phew. Okay. And the seventh derivative, negative cosine x. So I need to go through and I need to evaluate all of these things at x equals 0. So I want to evaluate every single one of those derivatives at x equals 0. Those are the numbers that are going to go up here. So sine of 0 is 0. Plug it in. Cosine of 0 is 1. Let's go plug it in. Sine of 0 is 0. Let's go plug it in. This one comes out to negative 1. Plug it in. And again, you are going to notice a pattern. So I am back to the sine of 0. Or I'm sorry, yeah, sine of 0, which is 0. Cosine, which is 1. Negative sine, which is 0. And then negative cosine, which is negative 1. And I'm done. Circle it. I have just written a seventh order polynomial that will mimic the sine function. Now, you may notice upon close inspection that every other term goes away because it has a 0 numerator. You may notice that all of the even terms go away. And what we are left with for sine x is, this is literally just an x. This is a minus 1/3 x cubed. This is a positive, 1 over 3 factorial, 1 over 5 factorial x to the 5th. That is a negative 1 over 7 factorial x to the 7th. And I'll bet you can guess what the next term is. Again, notice, look, I have all odd powers and I have alternating signs. My next term is going to be 1 over 9 factorial x to the 9th. The next term is going to be minus 1 over 11 factorial x to the 11th. And just like that, it took 4 minutes. I wrote an 11th order, actually, polynomial that mimics sine. So let's take a look at what we have just done. Here is your sine graph. Prepare to have your mind blown. There's my first partial sum, right? This is just the graph of x. Not great, but actually not terrible. Look, around 0 where we centered it. It's pretty good for a while. Okay. That's what happens when I add in the x cubed over 3 factorial. So again, this is just x. This is x minus x cubed over 3 factorial. Oh. I add in the x to the 5th term. So this is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Look at this polynomial. Tell me that's not cool. You can't tell me that. Here's my 4th partial sum. So I'm taking x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and subtracting my x to the 7th over 7 factorial. And again, look what it does. Changes the end behavior of that polynomial. When I go out to my 5th partial sum, again, look at this. This thing is hugging the sine curve, and we're out past -3 to 3 on the interval. Right? That's really cool. So I'm only right here at a 9th order polynomial, which took me 4 minutes to write, and I can approximate pretty much a full cycle of sine with my polynomial and be pretty spot on. So if you don't find that cool, then you need to like reevaluate your priorities. That's all I'm saying. Okay, so remember earlier when I said that whole derivative integral thing is like not really ideal? Well, check this out. We now know the derivative. We now know the Maclaurin series for sine x, right? We're memorizing that. They ask you for the Maclaurin series for sine x, you write it down, right? We know it. It's all the odd orders. It's alternating odd orders. Okay, now let's think about this. Cosine is the derivative of that. So let's take the derivative of that series, shall we? The derivative of x is 1 minus, I'm going to leave my 1 over 3 factorial here, and I'm going to take the derivative of x cubed. That is 3x squared. Okay, plus I have a 5 factorial. Take the derivative of 5x or x to the 5th, you get 5x to the 4th. I have a 1 over 7 factorial. The derivative of x to the 7th is 7x to the 6th, and so on and so forth. What I want you to see happens here is notice I've gone from odd order to even order, and even your factorials change because 3 factorial is 3 times 2 times 1, right? So this 3 cancels with the 3 in that 3 factorial, and it becomes 2 factorial. This 5 cancels with the 5 in 5 times 4 times 3 times 2 times 1, and this just becomes 4 factorial. This 7 cancels with the 7 in this factorial, and it becomes 6 factorial. So sine is all of the odd powers with the factorials alternating. Guess what? Cosine is all of the evens. And the way that I remember them, which is literally that if you take the derivative of sine, you get cosine. So it has to be that sine is the one that starts with x, because if you take the derivative of x, you get 1. So that has to be your cosine series. That's how I remember them. But literally, these two are on a list of ones that we just memorize, and I'm going to show you some really cool tricks that can shortcut writing Maclaurin polynomials. Okay. Let's do it. Let's write the 4th order Maclaurin that approximates the cosine of -3x. All right, so 4th order. So I'm going to say P4 of x, and I'm going to write my shell of my series out to the 4th power. So something over 0 factorial x to the 0. Now, I'm already pretty sure that I'm going to end up with only my even terms here. I'm pretty sure these derivatives are going to be 0, but I'm not going to not write them. All right, so let's take our derivatives here. Oh. Okay, hold on. Keep everything. Okay. I am back in business. Okay. The cosine of negative, oh, the cosine of negative, oh my God. You missed watching me struggle with my whiteboard. Negative 3x. Okay, so when I take my first derivative, the derivative of cosine is, of course, negative sine, but don't forget the baby. So this ends up being 3 sine negative 3x. Okay. My second derivative of sine is cosine. I have to chain rule a negative 3 again, so I end up with negative 9 cosine negative 3x. My third derivative, the derivative of cosine, is negative sine. So, okay, I'm afraid I'm going to miss a sign if I don't. The derivative of cosine is negative sine, so negative sine negative 3x, chain rule times negative 3. So I have a negative 9 and a negative 3, which is a positive 27, but I have this negative hanging out, so negative 27 sine negative 3x. And then last but not least, the fourth derivative. Let's see, derivative of sine is cosine. I'm going to have a 81 cosine negative 3x. Now, again, when I evaluate these at 0, all of my signs are going to go to 0, right? So this one's going to go to 0, and this one's going to go to 0. When I plug 0 in here, this is going to be the cosine of 0, which is just going to give me a 1. This is going to give me a negative 9. This is going to give me an 81. So when I plug my numbers in, you'll notice we were correct in our assumption that the odd terms would go away. But notice that my coefficients are a little bit different now because there was a chain rule. Okay, so again, this one is a 0 and this one is a 0. So my final answer for my fourth order, not that I would ever simplify, that's crazy, but sometimes you'll see right the first 4 non-zero terms, and so I don't know what they would say if you left those terms in. This term, be careful, this is not 0. X to the 0 is 1, 0 factorial is 1. This is 1 over 1 times 1. It's a big fat 1. Okay. Then I have minus 9 over 2 factorial x squared plus 81 over 4 factorial x to the 4th. I realize that 2 factorial is just 2, but I refuse to stop writing factorial because it's just a pattern, and so I don't want to not write it. Okay, so there's my fourth order polynomial. Okay, I'll put up a sheet of practice just writing maclaurins. Tomorrow we're going to address, or next, I don't know what day it will be, we're going to address those shortcuts that I was talking about with maclaurins, like the sine and the cosine series. There's also one for e to the x that we can memorize, and then we can kind of mess with them so that we don't have to do any derivatives. It's pretty cool. And then we'll talk about centering them not at 0. After that, we're going to look at more convergence stuff. Okay. I'm done talking to myself about calculus for the evening. Have a good day, night. I have no idea when you're watching this. See you later.